Okay, so the main goal of this talk this afternoon is to introduce you the Linuxboot continuous integration effort that we are driving as an OCP community member. Linuxboot aims to be an alternative system BIOS infrastructure to startup servers. And this is based on the Linux kernel, as you might imagine. And one of the goals is to reduce to the smallest footprint as possible on the proprietary software code required to bootstrap a server or network switch or whatever, and then hand over to the Linux kernel as to benefit from the PCI Express and all the device drivers we can have within the kernel, and as well the system security that everybody knows. Just as a quick introduction, the continuous integration infrastructure is definitely a work in progress. So everything is public from the hardware to the software side. So you will see that we will be speaking about hardware, even if a continuous integration platform is supposed to be a software infrastructure. And feel free to collaborate. Everything is on GitHub. So there is a Linuxboot repo, and you can go to that repo, and we have a sub-entry called Linuxboot CI, I think, if I'm not wrong. And the intent of the CI and the main goal is to be able to validate that we can replicate build. So that's something which is very important in the firmware industry. So if you have an end user which is facing some issues and you do not have a good track of record regarding your versions, you have to be able to be to rebuilding the infrastructures even a couple of months or years later. And that's really key within the CI. And the CI is intended to be connected directly with the GitHub account from Linuxboot. So the primary goal is each time a community member is going to push for a pull request, so new code integration within the repo, the intent is to test on real hardware that this pull request is not going to break everything. So we are trusting our developers, but I think if you want to trust people, you really need to be sure that what they are bringing to the community is really working. So the intent is not to refuse any pull request, but is to be sure that it is doing what it is supposed to do. To do that, so we are building a fully automated testing environment, and we are testing on real hardware. So up to now, the way we are testing pull requests, and stop me, David or Andrea, if I'm wrong, but we are building on the traditional CI infrastructures, and we validate that the build works. And then the best case is we start on QEMU, the new firmware interface, and if it boots, everything is OK. So unfortunately, for the last build, everything was OK on QEMU. And I was at a conference about 2 weeks ago, the OSFC conference, so some of you were there. And this was broken on real hardware. So there is always some tricky things happening between emulation and real hardware. And we need to be sure that the firmware works on real hardware, because this is the main intent of firmware. One of the challenges we face is we are expecting to support all OCP hardware platforms. So from starting with Winterfell, who knows Winterfell here? Oh, we got one guy, two guys. OK, so this is the Xeon V1 and V2 platforms from OCP community. So this is pretty aging systems, but we still have a lot of end users which are using them. And unfortunately, this machine is no longer supported by the ODMs. And this is increasing security risk when you use this kind of platform, especially when you see bugs coming up like Intel Spectre or Meltdown. So how can we keep this machine up and running? So does the end user have to trash them or not? And that's why we want to have Linuxboot being able to work on this kind of machine. So we have successfully booted Linuxboot on Winterfell, Leopard, Yosemite, Tiogopass, and I shouldn't forget the network switches, the wedges. So and this is a wide range of hardware platform, and the intent of the CI is really to be able to support all of these platforms. So right now we are not at this level of quality. So we just do support a single node, which is based on Winterfell. But really the intent is to expand that as fast as possible. But it will be depending on how many people can work on the project. So regarding the architecture, we didn't reinvent the wheel. So we just defined a web API. So this is the way we are expecting to interconnect the GitHub repo with the Linuxboot CI infrastructures. So through this web API, a couple of commands can be issued, so including build and so on. So we will see later on what kind of command the end user might be able to do. So the web API is launching command to a job controller. So and the build is a test is roughly based on building a firmware image, and then validating that firmware image is not going to break the node. So which a node break means when we turn on the node, nothing happens, or something happens, but the node is not usable. So that's really key. And then we want to go further. So what does it mean? So we want to test the basic features. So which means does the firmware has properly set up the node? Do we detect properly NUMA configuration? Do we detect properly power state configurations? Or can we see the PCI Express devices, and are they all there? So there is some tricky things on servers. Who knows PCI bifurcation? Oh, okay. So this is a way to reconfigure a PCI Express slot. So you're probably aware that PCI Express works with lanes configuration, so multiplied by 1, 4, or 16, and 8. So on OCP servers, we do have on Winterfell, Leopard, and most of the dual socket generation, just one PCI slot with a riser card. And the riser card is able to provide either full lane system configuration to a single slot, like 16 lanes. And if we want to spread these lanes to 2 slots, we have to use within the system BIOS a thing called the PCI Express bifurcations, which is spreading the lanes between the slot 0 and slot 1. So this is the way it works on Winterfell machine. So right now there is it's not a bug, it's a non-implemented features on Linuxboot. So we do not support PCI Express lane bifurcation, and that's why if you use PCI Express with Linuxboot on Winterfell machine, you have to stick your PCI Express card within slot 0, otherwise the card is not detected. So this is this kind of features that we need to test. So we need to have a bunch of nodes which are able to be reconfigured and automatically detected. Then after basic system validation, we quickly discovered we might be facing other unfunny things. So we need to boot an operating system. So roughly, as a firmware engineers, we are thinking that when the hardware is up and running and you can get access to graphic adapters, so your job is done. So that's not totally true. So you need to be sure that you can install an operating system. And at the early stage of the project, we quickly discovered that we were able to install CentOS, but we faced issue with Ubuntu for various reasons, like serial port system configurations or ACPI bad behaviors. So that's why we think that within the CI, we must go up to the stage where we install an operating systems and we validate with a couple of benchmarks that the performance of the nodes is reaching the level of performances that everybody is expecting from it. So a basic bug into a NUMA system configuration can imply bad hierarchy routing. So we can have most of the hierarchy routed to the bad core and involving poor networking performances. This is just one example. Or we can have bad memory bandwidth. So we really need to avoid that. So that's also something important. And we faced that many times during the Linuxboot project initial phase. So speaking about the implementation, so what was really key to us is to have something which was scalable, because from the beginning we were aware that we will have to test not one node but many nodes. And even when we speak about a single infrastructure, just picking up Winterfell or Leopard, so we do not need a single Leopard. We have many different system configurations to test, and some of them are not compatible to each other. So meaning that we will have to deploy that on many nodes. So that's why we wanted to have something which was easy to deploy and which was automatically deployed. So we used Ansible. Who knows Ansible in the room? that's better than PCI Express bifurcation. So you're mostly software guys. Stop me if I'm wrong, Guillaume, but I think most of the deployment process is based on Ansible. So you need to have an Ansible masternode, and then you can deploy automatically your own infrastructure. So we wanted also to have the CI being available as a standalone system. So because we want to be able to provide high quality software testing to OEMs which are working on next generation platforms. And what is key is even if the CI is public, and even if the first version of the CI can be accessed publicly and will be available publicly. So if you are Intel or an OEM who is working on the next generation platform, you don't want to share with a global community that you are facing either issues or you are beating everybody on something else. So up to the time the product reached the market. So that's why we wanted to have this opportunity and to bring the CI to people who wants to run it inside their own lab. So that was a key component. We have automatic redundancy, so because we are expecting to break nodes. So if the CI fails, if a node is in a break state, and if we cannot recover the node, that might be an issue. So that's why we use a batch scheduler, which is going to address a bunch of nodes and waiting for feedbacks from the nodes. And we are able to be reliable even if we have failures. And everything related to build is based on virtual machines. So we do provide to our developers VMs where they can define their building environment for either building the Linuxboot image or the operating system image. So just to fix the Ubuntu boot on Linuxboot at the early stage, we had to rebuild the whole installer from Ubuntu. So it could look like simple things, but it ends up with, I think it's about 3 hours build time on a 20-core server. So that's not a fast process. So it's taking a lot of time and does require us a lot of dependency. So that's why we quickly forgot the idea to use bare metal build and using VMs. Like that, we are fully independent from the basic operating system that rely on the CI. Just quickly as a basic setup requirements, you need at least 4 nodes. So the Ansible master nodes and Slurm controller and batch nodes. So they are for the batch scheduler. Who knows Slurm in that room? Nobody knows Slurm. So we do not have any HPC engineers here. So I think, David, you might be knowing Slurm. Are you sure about that? OK, Slurm is a batch scheduler. So that's a tool which is just queuing a bunch of jobs, and that is sending the jobs on a cluster node. So roughly, this is developed for supercomputers. So when you get thousands of users trying to address hundreds of thousands of cores, how do you allocate the cores to the end users? So roughly, you describe your jobs, you require for a bunch of CPUs, a bunch of memory and I/O, and you don't lie, because otherwise the batch scheduler is going to kill your job. So you have to be fair with the system. And when the related hardware is available, so the job is kicked on. So we are using that things because if we have a lot of PR coming up on Linuxboot projects, we just need to queue up the jobs because all the testing could be super long. So that's one of the issues. Moving forward, so the Web API, what can we do with it? So right now we have a first implementation of that. So you can you can describe a jobs, and you can get as an input a GitHub repository where you have your build environment which is pre-set up. So you can launch the build job, you can kill it, you can list it, and you can have a look to the build log. So this is roughly what the Web API is able to do. So this is validated for either building Ubuntu installer or Linuxboot images. So that was something important. All the Web API is currently written in Go. So don't be afraid about Go. So that's a language which is promoted mostly by Google and currently Facebook, or mostly Google, I think. But it's pretty efficient to write a Web API. So we currently support job launch, status query, and job log. So the controller, as I said, is allocated the nodes and preset the build environment. So that's also something important. So as we want to be replicable, so we need to preset always the same build environment. And we are storing through the controller the job status. So another time we are describing within that all the basic building blocks within the CI. This is just to ease you the access to the GitHub repo if you want to participate to the project. I'm not going in the right direction. Where I am, okay. Yeah, we have two classes of VM currently. So for Linuxboot build, we are using in-memory VMs. So most of the build nodes have 64 gig of main memory. So we have two main benefits to do that. First, the build speed is far much faster. And second one, we don't kill the node because most of the I/O are write operations. And if we are keeping writing on either SSDs or hard drives, we can kill the device. And that's totally stupid. And if we need more storage space, currently we do not have nodes with 256 gig or higher memory. So we write down on hard drives. So that's the thing. So we got these two classes of VMs. All of the VMs have access to the internet. So if you are developers, you can update some packagings if you need to update packagings, or you can get access to the internet for specific features you might be requiring. The controller is also copying the content of the build to the VMs, and then it starts the job. So that's the primary systems. So the builder is building the Linuxboot image. It's able currently to build most of the motherboards supported by heads. So the builder is based on heads project. Who knows heads? 3, okay. So within Linuxboot, you get two user space environments. So because when we start the system BIOS, we are starting a Linux kernel. So then after, we need to have user space environment. The Linux kernel by itself cannot do that much except initializing the hardware. So there is currently two implementations of user space. One is in C through the BusyBox infrastructure, and the other one is based on Go. And the C implementation is called heads, and the one in Go is called uroot. I was going to say nerf, but it's uroot. We have too many names, so if we have somebody who works in marketing in that room, it might be good. So because we're not really good at naming projects and sub-projects, we really need some help on that. And so we use heads because the Tramel Hudson from 2 Sigma has made a great job on the build environment. And we can build from heads everything based on makefiles. So I'm more than 40, so I'm a big fan of makefiles and parallel makefiles. If you are younger than me, you will hate me, but at least I got something which works. So that's the beginning. If you have something better that works, I'm ready to integrate that into that environment. But if it doesn't work, don't speak to me. So, so we need something which works. That's really key. So just to build, we face some slight IP issues. So when we are building Linuxboot, we are tweaking system BIOS image. So up to now, you are not allowed as a developer to push for a system BIOS to the CI systems. That's only because we don't know from where the image comes. So you are able to build only for a target that we own and for which we can process the build and we can test. So right now, the only one target that we support is the Winterfell node, but another time we are trying to expand that as fast as possible. So the CI has its own internal ROM currently, and you can tweak it. That's the stock ROM from the Winterfell node. So this is just a flash dump using a Dedupro programmer, and you can tweak it, but you cannot get the result back to you. So that's the key things. The output of the CI will be it works or it doesn't work. So you will never get access to the ROM file. So that's the thing. So except if you own the ROM file and you run it in-house in your lab. So we can build the nerf environment and we can build the heads environment. We are currently testing only nerf. That's because that's the uroot. Sorry about that. I need to upgrade that slide. So we can build the uroot environment, and we are testing that one mostly. And you can predefine which Dixie drivers you are willing to keep inside the image. So up to now, the default configuration is removing everything which is not mandatory. And we are keeping roughly the SCPI table generation stuff, SMM stuff, and a couple of few things that we cannot remove, otherwise the system doesn't boot up. So I think there is something related to the CMOS setup. So when we change the system BIOS, in some cases we got some not blinking, which requires that CMOS being reset, and there is a piece of code within the original firmware which is doing that. So if we remove it, it doesn't work anymore. Then the funny things happens. So we start the image. So the primary goal was to test on QEMU and then on real hardware. So we have a real hardware which is working, and we will try to make you a demo if it works. Just crossing the fingers. And regarding the basic feature validation, so one of the ideas is to test that we can PXE boot the nodes, and we can boot on the local storage nodes, and we can detect local storage. So we had a bug on Winterfell where the AHCI, not drivers, but the AHCI implementation didn't recognize properly the SATA devices. So we had a dirty workaround within the Linux kernel just to make it work properly. And just to give you some update on our booth downstairs on IT Renew, if you want to see a Winterfell node booting on the NVMe, so this is the demo that we have. And if you go up to the Facebook booth, it's not that far away from us, so you can see a wedge booting on core boot and Linuxboot. Then we can test the OS installer. I'm just going to go quicker and through that slide. And the intent within the OS stability and test is to run some basic benchmarking. So this is roughly the LeanPack benchmarks. Who knows LeanPack? Okay. That's a scientific computation benchmarks, which is roughly solving an n by n problem. So that's algebraic stuff. And we are also running Piston and some networking and Bunny. So the goal is really to run basic performance testing and validate that we are reaching what we are expecting. So that's really important. So then we thought at the early stage that we didn't need to make any hardware regarding Linuxboot, and that's not true. So testing firmware automatizing firmware testing requires that we adapt the hardware. So that's a debate we open also with the server community, because we would like to have all of these features readily available on standard OCP server, but that's not the case. So we had to tweak them. So Guillaume, it's up to you now.
Thank you. So when we talk about CI, as a software engineer, we are used for years now to use any kind of CI platform. But usually when we build software into a CI, we are building software that run on top of another software. For instance, you run a binary running on an operating system, or you build a Java application running into a Java virtual machine, and so on. When you're building a firmware, it's different because your software is not running on top of another software, it's running on a firmware, on a hardware. The issue is, as Giamarchi stated before, at some point you have to run it on a real hardware. If you don't do it, it will be broken. At some point, it's 100% sure. So what we are doing here is to be able to test the firmware on a real hardware, but in an automated way. So we need some tools, some hardware tools to do it. Here in our lab in Paris, we have 2 Winterfell nodes. One is the Winterfell node on which we will really run the firmware we just built. And the other one is a controller node to orchestrate all the scenario. So you can see on the controller node, there is 3 USB devices. One USB, the first at the bottom is an emulator. The emulator is plugged on the other side on the SPI bus in place of the BIOS chip. Then we have a microcontroller to be able to turn on and off the server without using any kind of remote management system, because in Winterfell, the BMC is already tied with the BIOS, so if we break the node, we are sure that the BMC won't work anymore, so we need to be able to turn on and off the server from a power perspective. And the last USB devices is just a FTDI adapter to get the serial port of the Winterfell nodes connected to the controller node. So this way, we should be able to test a ROM we just built. So let's see the live demo. Just need to. OK, here I log in onto the controller node on 3 shells. So here, on the first one, with this command, I will run the emulator, giving it a file, which is the ROM just built by the CI. OK, now the emulator is ready. On the other console, I will listen on the serial port. And now you have a script used to. No.
I did it last time.
So the script relay power on, power off. It will just send a signal on the GPIO and the microcontroller to power on and power off the server. So now I will just first do a power off just to be sure the server is powered off. I think it was the case, but who knows? So now I power on the server, and we will see on the left, OK, the board started to fetch the firmware from the emulator. And in a few seconds, on the right screen, we will see the boot from Linuxboot.
If everything works.
Yeah, it will. OK, some debugging information. I think it should be faster. OK.
I think the network is.
Yeah, some.
So.
No, but currently on this setup, we have some small hardware issue on the USB side. So at this point, on the right, the Linuxboot firmware is booted. We got the prompt. Then, if we're able to do that, we should be able to now do any kind of testing. In this demo, we just stop at the firmware level, but we could build a firmware that do many things. For instance, build a firmware who then try to boot an operating system using Pixie or any other boot from a hard drive or from any other kind of network boot. We could also build a firmware embedding SSH server or HTTP server to interact with the firmware, to fetch data, to run scripts or run a binary on the firmware and test everything is OK, make some assertion like we are used to do in any kind of software testing. And now using this system, we are able to orchestrate this, automate this, and put this into a build to make sure we don't have any regression on the firmware during the build of any revision from GitHub. So that's it for the demo. Just power off the server, and it should stop to fetch data, and that's it. The server powered off, and we can do it. And then this architecture is replicable, depending on how many workers we need to test builds in concurrency. It's pretty easily replicable.
Yeah.
Thank you. And no, it could be different. Currently, on the Winterfell node, we have only 2 USB ports. Here is just a small USB hub, but we could have, with one controller node, we should be able to manage a lot of Winterfell target testing system. But currently, just because it's more easy to start and more easy to set up, we did it this way. But it could be different. So okay. Let's go back to the slide deck. Oh,
that's fine. Okay.
Right.
Move forward. So the demo worked. That's pretty unusual. Thank you. Now that's a tricky thing. So we had some bad hardware behavior just to set up this kind of demo and environment. So one of the issues we face with this kind of CI is very basic one. So if we want to scale, we need to have more hardware. Hiding that in data centers and try to scale as much as we can. So we are just trying to figure out how to scale. How many of you are aware that the Linuxboot project is also part of the Linux Foundation? That's not bad. So we work with the Linux Foundation to try to figure out how we can scale the CI and keep it not free, but keep it accessible to anybody who is willing to develop firmware on top of Linuxboot. And so right now we just developed a few ways, but I think we are going to seek for sponsorship. So roughly, the Linuxboot project has currently a technical steering committee, and we have a general manager, which is who is Ron Minnick. And so we spent some time discussing as a community how we can scale it and how we can build something which is valuable to get access to the CI to everybody. So right now everything is set up in Paris, so the latency might be a little bit long for some end users who are based in the Bay Area, so we are thinking about starting some nodes there. But we definitely need more hardware just to test deeper things. We also started to look at how we could adapt the technology to OpenBMC, so which in some way requires some kind of feature. So if the BMC doesn't start, nothing works. So we just started to look at the Leopard infrastructure, which has an ASP chip and doesn't rely on the ME controller for remote management. And we think we will adapt the technology in a fast way to this kind of nodes. But whatever happened, so we need to work on a business model. And when I say business model, it's not making money. This is how do we sustain the infrastructure to make it work and keep it available for general usage to end users. So don't be surprised if within the next couple of weeks or months you will see coming up some emails from myself requesting for sponsorship just to sustain the infrastructure. I don't know yet where we are going to put it up, but there are some ongoing discussion with the Linux Foundation, and we're just trying to find out if we can work with other projects which might have the same requirement. So just to give you a rough idea, building up a full rack for a CI testing is about 10K per month. So that's a lot of money. But this is what is required between the flash emulators and maintaining the racks and hosting the racks, getting the power inside and all these things. So it's not a crazy amount of money, but that's still money. And we need to find something sustainable. What should I say? So as a conclusion, this was work that we started about a couple of months ago. So at the early stage, I didn't believe we could make it work in such a fast way. But we started to use the tool internally, and I think this is extremely efficient. How many of you have ever tried to develop firmware and reflash with a DediProg? Okay, so you are aware that it's not a mess, but this is unpleasant. You have to remove the chip, you have to plug it back into a small socket adapter, turn on your DediProg adapters. Everything takes time, so it takes about 10 minutes to reflash and restart, and just to conclude that you break the node. So that's really unpleasant. You lose time, you break hardware. So that's also why we work on the CI, just easing the process of testing firmwares and getting more general purpose developers getting interest to firmware development. So I think it's really key, and this is a good match, I think, with Andrea and David talk that they ran this morning about turning on your Linux engineers as a firmware engineers. So with this kind of tool, your Linux engineers doesn't need to know anything about DediProg, or it doesn't need to upgrade the USB drivers to make work properly the DediProg device. So it just need to have a laptop and launch a bunch of API commands. So that's the primary goal of that project. We are done with the talk. I think we are just on time. at least for finishing the talk. So we are ready to take some questions. I don't know if you have any questions. Oh, everybody fall asleep. I think, pick up the mic because that's for the recording. Sorry about that.
When you're asking about contributions, you're asking for money or you want infrastructure?
I think we will be more asking for money because IT Renew is getting access to a lot of infrastructure, so we can provide the infrastructures, but we don't know yet how we can recover the energy cost, the internet access cost, and all these things.
Like you know my setup, so it's already paid. It's
Yeah.
already available, and I can have spare servers running there.
That might be good. So if you are ready to pay for the energy and the connectivity, that might be great.
It's already paid. So.
So that might be a good option. Roughly, we are currently working on a specification document on what should be the infrastructure required to run properly the infrastructures. And when we will have done that, so for sure we will discuss around how to set it up properly. So but definitely we will be needing helps from outside. Any other questions?
What question? No?
We are going to finish a little bit early, so but hope you enjoyed the talk. And if you have any questions, we are on IT Renew booth and Facebook booth up to the end of the show, so which is in a couple of hours. Thank you for your time.